Hello, everybody. This is Bert Dixon here, presenting today on the first two sections of Chapter 10, which is on correlation and linear regression. And so the whole concept of correlation has to do with whether we have two data values that are related to each other somehow in some mathematical way. So, for example, in this table, I have student grades based on the number of hours a particular student um, studied. And so the first student studied for 6 hours and got a grade of 82. The second student studied for 2 hours and got a grade of 63%, and so on throughout the table. So one might assume that the students who studied more got a higher grade, and so that would suggest um, some kind of a positive relationship, meaning as the number of hours of study increases, you would expect the grades to increase as well. And so we can test that mathematically to see if there truly is a relationship. Okay, so that relationship, if there's one that exists, we call that correlation. And so when we plot data in a scatter plot, there are different types of relationships that we might witness, and that is one like this where there's a positive linear relationship. So you can imagine drawing a line of best fit that does a pretty good job of fitting the trend of the data. Positive meaning it has a positive slope. In graph B, it's also a linear relationship, but it's a negative slope. So in this case, as the independent variable x increases, the dependent variable y decreases. So as one increases, the other decreases, and that's called a negative linear relationship. So that can be considered a very strong relationship as well if the data is very linear, but if it has a negative slope, then we call it a negative linear relationship. So don't think of negative as being bad or a poor relationship. It just means that it has a negative slope. Okay. And then in graph C, sometimes we have data that there appears to be a clear relationship, but it might be some kind of a curve. And so we call that a curvilinear relationship. For example, in this one, it might be a parabola, or we might have other curves that fit, maybe an exponential type curve or something like that. And so in today's lesson, we're going to focus just on the linear relationships. And then graph D, as you can see, it doesn't appear that there's any kind of a relationship. It's hard to see that there's any type of curve or line that does a good job of representing the data. And so that would mean there's no recognizable relationship. Okay, so when we're talking about correlation, there is actually a coefficient that we can calculate mathematically to determine how well the data fits the line of best fit. So we can always mathematically come up with a line of best fit, but it may not be a very strong fit. We might have, data like this that are kind of spread out. So there might appear to be some kind of a linear relationship like this, but there's a lot of data points that are kind of far away from the line. And so what we can do mathematically is um, find the minimum sum of distances for all these points. How far away are they from the actual line of best fit? And if the average distances are small, then we get a good correlation. And if the average distance is large, then we get a poor correlation value. So that's called a correlation coefficient. We use the letter R for the correlation coefficient, as they say here. And so as I said, there's a way to mathematically find the line of best fit and mathematically find the correlation coefficient R. We are going to be using our graphing calculator to do those. So even though in the book they show the formulas, if you're interested in seeing those formulas, there are formulas in the book for calculating both the line of best fit and the correlation coefficient R. However, I'm not expecting you to use those formulas. I'm expecting you to use technology, which in this case is going to be your graphing calculator, to find the value of R and to find the equation for the line of best fit, which we call the regression equation. We'll get to that a little bit later. Okay, so the correlation coefficient R is always a number that ranges between -1 and 1. So -1 means there's a very strong fit. There's a good fit between the line and the data. If we're really close to -1, that means it's a strong fit. If we're really close to +1, that means it's a strong fit as well, but a positive slope. Okay, so if we're close to -1 or +1, that means the data is very linear. And then if it's not so close to -1 or +1, if it's something in between, like maybe from -0.6 to +0.6, or even -0.7 to +0.7, would not be a very good relationship. In fact, if it's a zero correlation, that means it doesn't appear that the data is linear at all. Okay, and so you can see some sample R values here. So in this sample here, the data does look like there's somewhat of a positive trend, but when we draw our line of best fit, it's not that tight. There's still a lot of points that are kind of far away from the line. And so that this data that you see in this sample has a correlation coefficient of 0.5. So it is a positive relationship, but it's not very close. Okay, whereas in example B, this is a pretty tight cluster of data that definitely appears to be linear. All the points are going to be pretty close to the line of best fit, so that has a correlation coefficient of 0.9. A correlation coefficient of 1 means the data is exactly linear. So when we come up with our regression equation, all the points actually fit the line exactly. There's no distance from the line, and so that would give you a perfect correlation, a perfect positive correlation of 1. And then in example D, we see the same kind of thing, but this one is -0.5 because it's a negative slope, not clustered very tightly. So these points are kind of far away from the line. And then if we have a tight cluster with a negative slope, that would be maybe about -0.9. And then a perfect linear relationship where the line goes right through all of the data, that would be -1, a negative because it's a negative slope. Okay, so the closer to 1 or -1, the better the data fits the line. So in our text in this course, we're only going to cover linear relationship, linear, the linear correlation and linear regression. There are other types of regressions. For example, if you felt like your curve, or if you felt like your data fit a curve that might be shaped something like this, it might be an exponential curve. And so there's something called exponential regression. There's also, if you think your data is maybe in the shape of a parabola, there's quadratic regression. There's also logarithmic regression. There's a lot of different types of regression. But in this course, we are only using linear regression. So we're only going to come up with the correlation coefficient if the data is linear. Okay, so here are some properties of R, the correlation coefficient. It doesn't have units. R is always between -1 and +1. If the values of x and y are interchanged, the R value will be unchanged. So it doesn't matter which, how you assign your values. If you put in data for list 1 and list 2, for example, and then you switch the x and the y, you switch list 1 and list 2, you would get the same correlation coefficient either way. So it doesn't matter what data you call your dependent variable and which one is your independent variable. Your correlation coefficient will be the same. And then also, if you change the scale, let's say you had data where you had maybe years that have gone by and salary or something like that. So let's say you had 82,000, 87,000, 96,000, 102,000, or something like that. Okay. So if you put in these as your x values and these as your y values, you would get the same correlation coefficient. If you entered these values exactly like they are, you would get the same correlation coefficient as if you did y in thousands. So if you entered it in your table in thousands, this would be 80 because it's 80,000. 2 would be 82 because it's in thousands. 3 would be 87. 4 would be 96. 5 would be 102. So if you entered this data in your calculator and found the line of best fit and the correlation coefficient, it would be the same. The correlation coefficient would turn out to be the same in both cases. So that's what they're saying here. If the scale, if we use a different scale, like this one was in dollars and this one was in thousands of dollars. So if we change our scale, that's not going to affect R. R is still going to come out to be the same. And then the last property is it says the value of R is sensitive to outliers and can change dramatically if outliers are present. So if you do have outliers, you may want to exclude them when you're calculating your line of best fit. That's something that the researcher would have to decide whether the outliers are, do they contribute to the sample or should they be ignored? Okay, so this is, as I said in the book gives you a formula for calculating the correlation coefficient. They also give you a long formula and a long process for coming up with a line of best fit, which you're not going to have to do, but it is in the book if you were curious how you come up with a line of best fit. Okay, so this leads us into 10.2, and so I'm going back to the same problem that we started with today, and that is this problem with relating the number of hours a student studies to the grade that they got on a particular test. Okay, and so we're going to first of all determine if the correlation coefficient indicates a strong relationship within alpha equals 0.05. And if the correlation is significant, then find the regression equation. Okay, so the first thing we want to do is calculate the correlation coefficient. And we're going to do that by putting the data in the calculator into list 1 and list 2 like we've done before. So we'll go to Stat, Edit, and list 1 I'm going to clear by highlighting the title and pressing Enter. And list 2, I don't have anything in list 2. If you do have data in list 2, you need to clear that as well. And so I'm going to put the hours of study in list 1, 6, 2, 1, 5, 2, and 3. And then in list 2, the y value is 82, 63, 57, and so on. Okay, so now that we have the data entered, we'll go to Stat, Calc, and we're looking for linear regression. Now there are 2 linear regressions on here. There's option 4, which gives you the form ax plus b, and there's option 8, which gives you a plus bx. It doesn't matter which one you use. Option 4 is matches the formula you used in high school for a linear equation, y equals mx plus b. So in this case, a would be your slope and b is your y-intercept. So that equation is used mostly by junior high and high school students because b is the parameter you always used for y-intercept. Whereas option 8 is the reverse of that. A would be your y-intercept and b would be your slope, which is not probably what you're accustomed to. But in this textbook, they do use A for the y-intercept and B for the slope when you're calculating it by hand. So if you have any of the Connect math problems that are asking for the parameters A and B, you might want to use option 8. So I'll go ahead and use that here. And so my X values are in list 1. My Y values are in list 2. We don't need anything from the frequency list. And then this step here, the storing the regression equation, is not required, but it will save you some time and accuracy by putting the regression, by storing the regression equation in the y equals menu so that you don't have to type it in to graph it. And so to do that, I'll go to the vars button. So vars, yvars, function, y1. And so that's going to store that once it comes up with the line of best fit, it's going to store that equation in the y equals menu so that it's ready to graph. And then I'll press enter and calculate. Now here it gives me A and B. Remember, A is the y-intercept, so this has a y-intercept of 54, and B in this case is our slope, which is 5.566. And so the equation of the line would be 5.5566x plus 54.54. And the R values are the correlation, the R is the correlation coefficient. So remember, if we're close to 1 or -1, that's a good fit. In this case, 0.92 is a pretty good fit. Now we're going to test it to see, is it close enough to use with our alpha value? We want alpha equals 0.05. So that's a pretty strict requirement. So we'll see, does this data fit well enough to use the linear regression equation. So let's first write down R equals 0.9217. In fact, I'll write down everything. So I have A is 54.54. B is 5.566. And we're using the form y equals a plus bx. So in this case, the linear equation, if it's a good enough fit, we would use 54.54 plus 5.566x. So again, that is our slope, and that is our y-intercept. Okay, and then the regression equation was, or the correlation coefficient is 0.9217. So R equals 0.9217. Okay, now if you do this on your calculator, I'd like you to go ahead and try it. Put in the data and do the same thing I did, which is that I went to Stat, Calc, and I choose option 8. Choose option 8. And if you go through this same process, but yours does not give you the R value, on some calculators, it will only give you the A and the B, but it won't give you the R value. So if that's the case for you, the way you turn that on is if you follow these steps, you press second catalog, and then we're looking for diagnostic on, and that's in the D's. So if I immediately press this button right here that has the green D, it jumps to the D's because it's all in alphabetical order. And otherwise, you have to scroll all the way through and look for the D's. We're looking for diagnostic on. So I'm going to keep scrolling here until I see diagnostic on. There it is. Diagnostic on. I press enter and then enter again. Now my diagnostics are on, so that means when I do the linear regression, and remember we said we want to store the regression equation using vars, yvars, function, y1. So when I do that, now if you went through those steps to turn the diagnostics on, you should see the R value of 0.9217. Okay, so now the question is this correlation strong enough to meet the threshold of alpha equals 0.05? And there are two ways to finish it from here to test it. One is to use the T table with alpha. And so if alpha is, this is always a two-tailed test when we're testing the regression. And so each of these, since alpha is 0.05, this would have to be 0.025 here and 0.025 here. And so if you do inverse T of 0.025, this comes out to be T value of negative 2.776, and then positive, same thing. So if you had put in 0.9, what would it be, 0.975, you would get positive 2.776. But once you get one of them, you know, the other one is just the opposite. Okay, so this is our critical area. If it's in here, then what we're going to do is we're going to reject the null hypothesis. Now, we didn't write down our null hypothesis, so let's do that. So our null hypothesis is going to be that the that the rho value, in this case, our correlation is 0. So we use R on the calculator, but rho, this Greek letter rho, looks like a P, but it's rho. The Greek letter rho is what we're using for the correlation coefficient. So this is saying the correlation is 0. That's the null hypothesis. And our alternative hypothesis is that the correlation is not 0. And if the correlation is not 0, then we're going to say it is a linear relationship, okay, within this threshold of alpha equals 0.05. Okay, so now we can calculate the t value a couple of different ways. I can use t equals using the formula that I mentioned up above. If I use that, we know our R value is 0.99, or sorry, 0.9, we'll call it 0.922, or actually we'll just leave it as 0.9217. And then it's the square root of the n minus 2. And notice that n minus 2 is also our degrees of freedom. And so if we do n minus 2, in this case, that would be 4. We have 6 data items in our list. So n minus 2 would be 4. And then we're going to divide by 1 minus r, which again is 0.9217. And if you calculate that, that turns out to be t equals 4.755. Now that is in our critical area. 4.7 would be way over here. That is in the critical area. So we're going to reject H0, and we're going to say that R is significant enough to use linear regression, to use the linear regression equation. Okay, and so this is our linear regression equation right here. And if R was not significant, in other words, if R ended up being in this middle area here, we would just reject this equation altogether. We wouldn't consider it a linear relationship. But now we're saying that R is strong enough that we're saying this is definitely a linear relationship. And so we're going to use this equation to, we could use this equation to estimate if somebody spent maybe 4.5 hours studying, we could use that to predict the grade that they would have gotten. Okay, so that was one way, was using the t equation. Now I said you don't have to memorize this t equation because you can also get it on your calculator. And so the other way to do this is to use the R value that we got. And there's a table called the PPMC table, and it's table I in your textbook. I also linked it on the course assignment listing on the table, and it's also in the student docs folder. Look for table I, the PPMC table. It looks like this. And so using this table, we said our degrees of freedom was 4, and this is always a two-tailed test, and ours was 0.05. So the value we get here that we're going to compare R to is 0.81 or 0.811. And so in this case, it says if the absolute value of R is greater than the given value, we're going to reject H0. Okay, so it tells you right here, reject H0 if the absolute value of R is greater than the given value in the table. So in this case, R is greater than, absolute value of R is greater than 0.811. This came from the PPMC table. And since R is greater than 0.811, we're going to reject H0, which means therefore R is significant, which means the relationship is linear. Okay, so I showed two different ways to get that. You could use the PPMC table to compare it to directly to R, or you can use the inverse t to set up this, and then calculate the t value using the formula that was provided up above. And so either way that you do that, we got the same conclusion, which is this data is linear, so we're going to reject the null hypothesis. Also, I wanted to show, now that we have all the data in the calculator, we can actually see how well this data fits. And so if I go to y equals, then I see, oh, there's an equation 2 in there that I don't need, but equation 1, notice that that fits. That is exactly what we said, A and B, because we told the calculator to store the regression equation. So if I scroll far enough over here, you'll see that this is going to say plus 5.5666 and so on x. And so that is our line. And if we want to see that line along with the data, then a couple things that we need to adjust. The window, since our data is, the data we see goes up to 6, so I'm going to say my x min is 0, and it goes up to 6, but I'm going to put it to 0 to 10 in case we want to try some higher number of hours. And then the y values were in the 60s, 70s, and 80s. So I'm just going to say from 0 to 100. And then if I graph, I get that linear equation. Now, what I don't see is the data. And so to get the data, if I go to stat plot, that's second y equals is stat plot. I want to turn these plots on. So I'm going to press enter and I'm going to turn it on. Notice that it's plotting a scatter plot. That's what the type is. This is a scatter plot. And then list 1 is L1, and the X's are in list 1, the Y's are in list 2. And then I'm going to use this little box to mark each point. And now that I have this turned on and I graph it, we see the data and we see the line, and we see that is a pretty good fit. And that's why we got an R value of 0.92, because that is a pretty strong positive relationship. So it's always good to see your data and see the line, and that confirms what we got mathematically here. Okay, so let's move on to example 2. So this time we have some data about the number of murders that were committed in a certain city, or in a state actually, and the number of robberies from randomly selected states shown. Is there a linear relationship? And so we're using, again, alpha equals 0.05. And so the first thing we should do is put the data in the calculator. And I'll show you another way, a third way that we can use that data in the calculator to get all the answers that we're looking for. And so I'm going to go to Stat, Edit. I'm going to clear list 1 and list 2, highlight the title, press Clear, Enter. Now I'm going to put in the values 2.4. Okay, now that I have all the data entered, this time I'm going to go to a different place in the stat menu. I'm going to go to tests. And there is, under tests, there is something called the linear regression t-test. And that's going to have everything that we need all combined into one. There it is. So on mine, it's option F, linear regression, linreg t-test. And so by doing this, we're not going to need to refer to table I. We have our data in list 1 and list 2. And in this case, we're saying that the correlation coefficient is not equal to 0. I'm going to store the regression equation as y1 again. So vars function y1. And again, you don't have to do that last step that I just did, the regression equation. If you don't put y1 there, you would just have to type it in manually if you wanted to see the graph. Okay, so now we're ready to calculate. And so this gives me, let's see. If I scroll down far enough, it gives me A, B, and R. And so I'll want to copy all of those things down. So B is 25.209. A is up higher. Let's see. There we go. A is negative 10.465. So that means the equation, notice it says A plus BX. So that's going to be negative 10, Y equals negative 10.465 plus 25.209x. So that would be our regression equation that we're going to use. If it is a significant fit, we're going to use that line a little bit later. Our R value turned out to be 0.8366. I'm going to check my lists and make sure I have those because I did get a different value last time. Let's see. Oh yeah, I see the problem there. That first point, the x value, I put in 2 and it should have been 2.7. So let's see what happens if I redo that. Okay, so if I change that to 2.7 and redo my test, remember we're looking for linear regression t-test. So let's redo that. Okay, so this time we got A is actually negative 13.15, which is what I got last time. So let's fix that. Negative 13.151. B this time turns out to be 25.333. And then our regression equation would be negative 13.151 plus 25.333x. And our R is 0.804. Okay, now the rho value, we can compare that directly to alpha. In this case, each end, remember each end of each tail is 0.025 because we're using a threshold of alpha equals 0.05. So each one gets half of those. And our rho value on our calculator, you can use that. This gave us rho equals 0.016. Rho equals 0.016, which is less than alpha. So one way to get our ruling on this test is to use rho. If rho is less than alpha, then we will reject the null hypothesis. So in this case, 0.016 is less than 0.025. In this case, it's actually alpha over 2. And so alpha is 0.05, but we're using alpha over 2. So if rho is less than alpha, then we, which it is in this case, then we're going to reject the null hypothesis, and so R is significant. Okay, the other way is to use the negative 2.776 again and 2.776, and use our t value, which is also right there on our calculator. It says t is 3.315. T equals 3.315, which if we put that in our t curve, it would be over here. So that is in the critical area. So again, since t is in the critical area, we would say R is significant. So we reject our null hypothesis, which our null hypothesis always says rho is equal to 0, and we're saying that since we're rejecting the null hypothesis, we're saying that rho is significant. Okay, and so R is 0.804, and so now that we have this regression equation, if we go back and reread the question there, by the way, there in our book they call this equation y prime. So y prime is equal to negative 13.151 plus 25.33x, and then it says find the regression equation and find y prime for the specified x value. No regression should be done if R is not significant. In this case, R is significant. So it's saying find y prime when x is 4.5. So y prime when x is 4.5 would be negative 13.151 minus 25.333x. X in this case is 4.5. And if you plug that in, you get 100.845. So this is showing, since we are saying R is significant, that's telling us there is a positive relationship between the number of murders and the number of robberies. And so as one goes up, the other one goes up as well. And so this, when we plug in 4.5, that's telling us if we have a city where or if we have a state where there are 4.5 murders per 100,000, then we would expect to have 101 robberies per 100,000 people in that same state. Okay, so that's showing that relationship, and so we can now use this regression equation to do predictions like we did here when we plugged in 4.5 and we got 100.845. Okay, so example 3 is very similar to that. So go ahead and pause your video and put in all this data in your calculator, and then do the under stat tests, you're going to do the linear regression t-test, and then use your results to decide if the data is significant, or if R is significant enough to say that the data is linear. Okay, so I put all the data for this problem in the calculator, and then I went to stat tests, and I went to option F, linear regression, and our null hypothesis. I realized in that last problem, I treated it as once it gave us the p-value, I said it had to be less than half of alpha, but since this is already taking into account when we say rho is not equal to 0, that's already making it a two-tailed test. So we can just decide whether p is less than alpha if we're using the p-value. And so in this case, we'll go ahead and calculate, and it gives us the t-value if we want to use that and use the t method. It also gives us p, which is p is 0.0017, and that is less than alpha. So that's all we need to say that this is a good fit. And so since if we use the p-value, the p-value here turned out to be p equals 0.0017, and that is less than alpha, which is 0.05. So this is enough to tell us to reject H0. H0 would be that rho is not equal to 0. So as I was saying, this already treats it as a two-tailed test. So in the last example, I think I said it had to be less than alpha over 2. I did that here. So it's actually the p-value on the calculator has to be less than alpha. As long as when we use that linear regression t-test, we can just use p is less than alpha. If p is less than alpha, we're going to reject H0. And so that's what we're doing here. It's already taking into account that it's a two-tailed test. Now, if you use that table I, you'll get the same result, because if we used the R value that they gave us, if we keep scrolling here, we get A, B, and R. R in this case is 0.88, which sounds pretty strong. R is 0.88, so a strong linear relationship. Now, if I use table I, in this case, we have 1, 2, 3, 4, 5, 6, 7, 8, 9 data items. And so if I use table I, 9 data items means the degrees of freedom would be 7. And we're using so 0.666. And so as long as R is bigger than 0.666, we're going to treat it as a linear function, or in other words, reject our null hypothesis. And so in this case, R is 0.88. That is bigger than 0.666. So that would be another way to come up with our conclusion here. You could say R equals 0.88, and from the PPMC table, we have R is bigger than 0.666, so we are going to reject H0 and accept the regression equation since r is significant, we're going to go ahead and use that regression equation that we get. I'm just going to create a little more space here. All right, and so our regression equation from the calculator, we had A is up here, A is 181.66, B is 7.319, and so our regression equation then would be y equals 7.319x plus 181.661. And since we are saying that it is a linear relationship, now they want us to calculate, find y prime. We're calling this y prime. Find y prime when x is 200. So if we plug in 200 here for x, we get 1645.403. Okay, so on the calculator, there's a couple ways you can get that. You can type it in just like that, but since we stored the regression equation as y1, another way to do that is to go to the home screen and do variables, y variables, function y1 of 200. And so that's just using function notation. So that's one of the advantages to storing the regression equation as y1, is that now we can use it. And it gives us that answer of 1645. So it's basically doing this math for you, just plugging it into the regression equation. Okay, and so that tells us that if the number of releases is about 200, if the number of commercial releases is about 200, then our gross receipts will be about let's see, this is in millions, so this would be about $1.6 billion. Okay, the same idea on example 4. Let's go ahead and type in this data and see if R is significant. And if it is, then we'll use the regression equation. And if it isn't, then we will accept the null hypothesis and say that there's no relationship. Okay, pause your video and go ahead. Okay, so I have the data entered, and now I'm going to do the same thing we did on the last problem. I'm going to go to stat, tests, and I'm looking for test F, the linear regression t-test, and accept all the same parameters that we did before. Calculate. This time, if we use the p-test, p in this case is 0.3717. Now, p in this case is not less than alpha. So since p is greater than alpha, we're going to accept the null hypothesis and say there is no linear relationship, or the linear relationship is not strong enough to use within alpha equals 0.05 within that confidence range. Okay, so that's one way. Again, we could do the same thing by using the t value. T is 1.04. So if we're using this, we have at 0.05, it's negative 2.774 and positive 2.774. And t equals 1.048, which puts it here. It's not in the critical region. It's not in the tails. And so that's why we're going to accept H0 and say there's no linear relationship. Or I'll say not a significant linear relationship. And so since there's not a significant linear relationship, we're not going to do this. We're not going to approximate the tax when x is 1500, because this data doesn't give us a good relationship between the two. So we can't make that prediction. And so on these problems where there's no relationship, you don't want to come up with the regression equation. Okay, and then we have one more to do. So again, pause your video, enter the data, and then press play when you're ready to compare. Okay, so again, I have the data entered. I go to stat, tests, linear regression t-test. And in this case, our p-value is 0.013. So if we were going to use the p-value, then we'd say since p is less than alpha, reject H0, where H0 is that our correlation coefficient is 0. We're going to reject that in this case and say our correlation is not 0, so there is a linear relationship. And as always, you don't have to use the p-value. You could use the t-value. T is 3.787. And so that would be with the same alpha value. That is 3.787 would be up here, and that is in our critical area. And so again, we're going to reject H0 and say there is a linear relationship. So R is significant. In this case, R turned out to be, if we scroll down far enough, R turned out to be 0.861. And A turned out to be 2.693. B turned out to be 1.962. And so we can, since we are saying there is a linear relationship, R is significant, then we can write our equation. Y prime equals 2.693 plus 1.962x. And now we're going to use that to approximate the total number of points when a player has 30 assists. So y prime of 30, 2.693, 1.962 times 30, and you can type that in just like this in your calculator, or since we stored the regression equation as y1, I can go quit and evaluate the function vars, y vars function y1 of 30. That's like saying f of 30, and we're plugging 30 into the function y1, and that gives us 61.56. So we'd say about 62 points. So that's telling us if a player has about 30 assists, we predict that they're going to score about 62 points. And that is it for today's lesson. Everybody have a great day.